Hello everyone, my name is Xingyu XU. I'm from Nanjing University, China. I went to EMPC for the optical fiber monitoring of energy pile, and my supervisor is Anming Tang, Jean-Michel Pierre. The duration of secondment is from September 22 to November 30. My presentation is divided into three parts, respectively are introduction, optical fiber sensing, and applications. To investigate the thermomechanical behavior and the effect of the energy pile, new technology must be developed to adapt to the monitoring demand of the energy pile test. In general, energy pile test needs a continued long-term monitoring and the test environment is usually under a continual temperature fluctuation, which bring a big challenge for the conventional monitoring sensors, such as vibration, wire gauges, and the resistance type gauges. Um, Here I introduced two in-situ tests that results have published into journal articles. The first one is the first one in-situ test was established in Lambeth College, London, UK. The optical fiber sensors were utilized to measure the strain and the temperature. Two test piles were monitored in this test. One was applied mechanical load and the other one wasn't being applied the mechanical load. The main test pile was cooled for 31 days, heated for 12 days, and then cooled and heated in daily cycles for 3 days. The thermal load applied to the heat sink pile was the reverse of that applied to the main test pile. Here are the distribution of sensors in the test pile. The second in-situ test was established in Lausanne, Switzerland. The special packaged optic fiber was applied in the test with traditional sensors. The load progress was divided into 7 phases. Each thermal test consisting of a heating and recovery phase was undertaken with a different head load, each test lasting for about 28 days. Here are the view of the test site in Lausanne, the soil profile and the instrumentation of the test pile. In EMPC, the group continuously does the indoor model test and prepares for the energy pile in-situ test. In the model test, they don't use the optical fiber sensing technology, and they want to use this new technology in their in-situ test. In my home university, our group named ACEI focused on the optic fiber monitoring and utilized this new technology in many model and in-situ tests. At the beginning, my secondment is to participate in the in-situ test. However, because the test postponed, I only joined the work of making optic fiber monitoring scheme for the energy pile. Here, let me introduce the optic fiber sensing technology. I choose three representative technologies (FBG, BOTDR, and BOFDA). In traditional monitoring technology, each sensor needs one line to connect to the analyzer, and it belongs to the point measurement type as the first picture. And FBG is one kind of quasi-distributed technology. Um, it can do monitoring with high frequency, and many gratings only need one line to connect to the analyzer, as the second pictures. BOTDR and BOFDA are the fully distributed monitoring technology, as the third picture. And for optical fiber sensing is divided into the quasi-distributed and fully distributed. Um, the principle of fiber Bragg grating (FBG) was first discovered by Hill. When the strain and the temperature was applied on the grating, the Bragg wavelength will change, which appears to be linear. This phenomenon was utilized for measurement, and the relationship of strain and temperature measured by FG is submitted to an equation. Here are the equation, and the diagram shows the FBG principle. We can, when the fiber is compressing or stretching, cooling or warming, the Bragg wavelength will change. Brilliant optical time domain reflector meter (BOTDR) is a distributed sensing technology that allows the strain and temperature along an optic fiber to be measured. This sensing technology is based on scattered light, which is caused by non-linear interaction between the incident light and the photons that are thermally excited within the light propagation medium. When this progress occurs in an optic fiber, the backscattered light suffers a frequency shift, which is dependent on the temperature and the strain environment of fiber. Here we can see the equation of the BOTDR, and the picture shows the BOTDR principle. When the strain and the temperature applied on the optical fiber, the light will change in the fiber. Brilliant optical frequency domain analysis (BOFDA) was developed to measure the Brillouin frequency shift by pump and stock light. When the frequency differences between pump and stock light waves is equal to the frequency of the sound wave, the transfer energy is the largest. Because the sound wave frequency is related to the strain and the temperature of optic fiber, the Brillouin scattering spectrum can be utilized to measure the strain and the temperature indirectly. This sensing technology can obtain the pulse response through inverse fast Fourier transform of complex baseband transfer function, which is decided by the pump and stock's intensities, and transfer the pulse response into the relationship between the space and the Brillouin frequency shift. This picture shows how the BOFDA principle works. talk about applications, I first compare these three technologies and show the installation techniques. As I said ahead, optic fiber sensing technology can be divided into two types, which are the quasi-distributed sensing and fully distributed sensing technologies. The FPG is belong to quasi-distributed sensing technology, while BOTDR and BOFDA are belong to full distributed sensing technology. Here the table shows the detail of three technologies. The quasi-distributed FPG has the best accuracy, with the fully distributed feature. BOTDR and BOFDA show some differences. BOTDR has long test distances, but spatial resolution and accuracy is low, and the BOFDA has good spatial resolution and accuracy, but with a shorter test distance. At the same time, BOTDR analyzer usually needs about 4 minutes to acquire the condition of optic fiber. For BOFDA analyzer, it is close to real time. In general, BOFDA analyzer is more expensive than BOTDR analyzer. FPG analyzer is the cheapest. However, when the test distance is quite long, the cost of gratings usually covers the advantage of the FPG analyzer price. Since both strain and temperature can affect the wavelength or frequency shift, the independent measurement of strain and temperature is the key of the accuracy of the energy power monitoring. These are special packaged FPG sensors for measuring strain, pore water pressure, earth pressure, and load. For the fully distributed optic fiber sensing technology, the specialized installation techniques were established to face the test demand. One is using free optic fiber coils for temperature calibration, and the other is using metal blowers to protect the temperature sensing optic fiber in the pile. Thanks for your attention.